Conquest in the sky. We are inside a flying laboratory where science is studying the birth and life of a star. And in this plane, we will make the first public test flight of a top-secret navigating system for aircraft, missiles, space.
Nation's leaders in man's progress into the future, creating chemicals, plastics, and petroleum products for industry, the farm, and for you. New knowledge about our universe, our world, and ourselves.
Now a word from Nelson Case. This is an electronic device that is going to take the place of a group of highly trained human beings.
35.2. Coefficient set.
On inertial and transfer power.
These men are hitching their wagon to a star. The wagon is this airplane. I'm Eric Severide. This is Hanscom Air Force Base near Boston, Massachusetts. We are going to fly from this airfield to Los Angeles, California, but it won't be like any flight that you or I have ever made. This is the first public test flight of a new and revolutionary method of navigation called inertial guidance. There's the equipment there. It's SPIRE. It stands for Spatial Inertial Reference Equipment. It's a kind of self-contained model of our world. Inside it, our course to Los Angeles has been fixed, preset among the stars. For nearly 3,000 miles, if everything goes well, it will take the place of our eyes, our ears, and our brains. These are some of the men who developed SPIRE. They are mathematicians, engineers, astronomers, physicists. They'll be along on the flight to check on the instruments and, of course, to be on hand if anything should go wrong.
Howdy, Eric.
Hello, Dr. Draper. I'll see you later in the plane.
Fine.
How does SPIRE work? What does it mean for the future of travel? We'll get some answers from these men during this flight. Minutes have now passed since we left the ground. We are now flying steadily at 10,000 feet. Up to this point, our takeoff and our flight have been normal, routine, under the control of our pilot, Chip Collins. But now the big switch is about to happen.
Are we ready to go on SPIRE control?
The reference ground track is set. You can line up your present ground track with the reference ground track, please. That will take about a 2-degree turn to the left, please.
Roger, stand by.
That looks good if you can hold it there.
Okay. Are you ready for Spire control?
Spire ready for control.
Roger, Spire control coming on. Spire constant altitude. Spire system has the aircraft.
Check.
For the purposes of navigation, this plane is now cut off from all outside communication. Spire has taken over. From now on, it's our pilot, co-pilot, navigator, our radio, our radar, our compass. As far as navigation is concerned, we could be flying in a sealed box, deaf and blind. Let's go up and talk to Pilot Collins about it. Chip, I want to disturb you a minute, now that you've got this thing flying on Spire. Everybody's familiar with the ordinary automatic pilot, which allows a human pilot to leave the controls from time to time. Now, what is the real difference when you add Spire to the ordinary automatic pilot?
As you well know, the standard autopilot requires intelligence to be put into it from the human pilot, or from the navigator, from the radar operator, or some outside source. If a wind, for example, should drift you off course or drift you off airways, you must do something to correct to get back on. Now, however, this autopilot is different in the respect that it will not let you get off course. Any extreme high shear winds or any tendency to drift off is corrected because Spire detects any effort to displace the missile or the aircraft in this case and will immediately make a proper correction. As you can tell by looking outside, we're under instrument conditions. We have no reference to the ground. The Spire system has been set up on our departure from Bedford on a predetermined course for our destination, Los Angeles.
And why do we need so many men along on this trip?
We are running a test flight to determine the minute accuracy of this system, and in so doing it's necessary that we have data to determine the detailed accuracy of our course.
Well, our pilots or navigators going to be out of jobs at this rate, Chip?
It certainly looks this way unless we can keep this testing up.
May not be out of jobs, you just won't have to work so hard.
Well, I'd like to think that's the case.
Well, I'm afraid I'm a little old-fashioned still, because I must confess, Chip, that I take more comfort in the fact that that gadget has you on board than in the fact that you have that gadget on board.
Thank you, Eric. That's a very kind compliment.
This is John Crapo, one of the flight test engineers. John, I've been watching you from time to time here, but I'm a little mystified about your function on this flight. How would you describe yourself? Are you doing a navigating job here?
No, I'm not doing a navigating job at all. The Spire system is doing all the navigating on this aircraft at the present time.
Tell me, what kind of outside checks are we getting on Spire's performance now?
We're getting two types of checks, Eric. One happens to be a visual check of the ground, the other a check by radar.
Are we taking a lot of them as we go along? Do we have some very specific checkpoints on the ground?
Well, generally, such points as cities, lake shores, rivers, bridges, highways, things like that make good checkpoints. And in, I'd say approximately 2 hours, we'll be going over Chicago, at which time we'll get a very good checkpoint on the lake shore there.
Well, you're checking the accuracy of Spire all the time as you go along, but you are not correcting Spire in any way yourself.
There is absolutely no correction being put into the system during the flight.
From the way that Spire's been behaving so far, John, are we coming in on spot, and is it a small spot or a big spot we're aiming for?
I'm sorry, Eric, but specifically I can't give you that information. It is secret. You will know, however, when we come over Los Angeles, but exactly what our target is, I can't tell you.
now been flying just about 3.5 hours. According to the gadget, according to SPIRE, at this time we should be in the vicinity of Chicago, Illinois, and I am happy and a little amazed to say that that is exactly where we are. Chicago is just over a bit to our left. A while back, the gadget said we had a tailwind following us since we were going west. Nobody really believed that, but the gadget turned out to be right again. Still flying straight on course. So far, no mistakes by SPIRE of any kind so far as we can tell. We've got a notion now of what it is that SPIRE does on this flight, but we've got to know more about how it does it and why it does it. The man who can explain that better than anybody else is the man who had more than anybody else to do with the development of SPIRE. He's the man that everybody in this crew refers to as the Doc. That means Dr. Charles Stark Draper, head of the Aeronautical Engineering Department of the Massachusetts Institute of Technology, and director of MIT's Instrumentation Laboratory, where most of this work was done. Dr. Draper, I'm sorry that we have cluttered up your plane, at least for a while, with these teaching models of yours, but I thought that was the only way to really make it clear to everybody, including me, just exactly what the basic physical laws are from which SPIRE has been developed. Would you show us here on the model what the starting point of this whole fantastic operation is?
Be very glad to, Eric. Here we have a prototype of all gyros. It's a demonstration model, obviously. I can start it spinning here with my hand. The actual device in the equipment, of course, is spun with motors, but this shows the principle. You have a gyro. This is the axis of the gyro, and the property of Newton's laws under which the wheel spins is that this axis, having been given a direction in space, will hold that direction no matter how the base of the thing moves. For example, if I pick this up and turn it this way, you will notice that it continues to point in the same direction. If I tip it this way and this way, it holds the same direction still. This illustrates one of the fundamental principles of the actual SPIRE system there. See, the SPIRE unit is set within frames or gimbals in such a way that it can keep its original direction in space no matter what the motion of the plane, yaw, roll, or pitch. The actual system contains elements of three types: gyro units, pendulums, and a clock. This is the way they work. Try to imagine a bird's eye view of our situation today. We have a starting or launching point. In our case, that's Boston. And we have a target. For us, that's Los Angeles. Before our flight, the SPIRE gyro package is aligned in space. As we start to travel, our SPIRE gyro package does not turn away from its original direction in space, no matter how the plane may move. Thus, we have at all times during the flight a permanent reference to our starting position. Now, here's the second basic component of the SPIRE system. A pendulum-like device so designed that it always points in the direction of gravity, that is, towards the center of the Earth. Let's assume that the gyro axis and pendulum have identical positions when we start. As we proceed on our preset course, an angle develops between the fixed gyro position and the changing pendulum position. By measuring that angle or arc at any given moment during our flight, we can tell exactly where we are and how far we've traveled over our course. The pendulums also tell us at any given moment if we're going off course. Then, as Chip told you, SPIRE directs our automatic pilot to bring us precisely back on course. Now for the third basic element. As we move through the sky, the Earth turns beneath us. We need to account for this. So we put a clock into the SPIRE system. With these elements, gyros, the pendulums, and the clock, SPIRE indicates our position at all times with respect to the Earth.
Well, watching that SPIRE gadget time to time, I still have a terrible time believing that it's not moving.
Well, it's very hard to prove it in the airplane because of the fact that we assume that the seat is standing still and that the SPIRE part is moving. Actually, if you look at it on the ground, you can move the frame around and you'll see that the middle part, the thing you see there, is actually standing still. See, this is standing still. The airplane is coming up. Now the airplane is going down. This is standing still.
I still have to take your word for it.
This is level. But now you will observe that before many hours that this device will have taken us to Los Angeles.
You have no doubt whatsoever that that little...
Not whatsoever.
That
Absolutely
little
not.
piece of astronomy in a closet there is going to take us right to Los Angeles.
That is right.
We've been flying now over 6 hours. More than half our trip is done. More than half the country has passed below us. The experts aboard assure me everything is working just right, that nothing is out of line. But I notice that Dr. Draper, Bill Gates, and the others are taking nothing for granted. After all, this is a test flight, and SPIRE is a complex, very sensitive device. These men have given it an almost unbelievable task. Dr. Draper, you've studied a lot of things in your life, including medicine, I understand, but how did you get started on this problem of navigation?
Through my interest in aircraft instruments, flying, and then we went through a period of working on gyros for anti-aircraft gunfire control.
Doc, has SPIRE got any possible peacetime uses?
In my opinion, yes. It represents a natural and very useful extension of the ordinary autopilot for airplanes. And then we'll use SPIRE to help clear up the jet-age traffic jam over our airports. SPIRE will bring planes more accurately into the airport control areas. We'll put it in ships of all kinds. We're already planning to use it in atomic submarines. For instance, with SPIRE as navigator, an atomic sub could cruise submerged for long periods with accurate knowledge of its position at all times.
What about space travel?
Well, in spaceships, you'll find this type of equipment is not only useful but necessary. It's already being used in some of our rockets, and when we really move out into space, some form of inertial guidance will be essential. Of course, the equipment would be smaller and lighter, but the principles would be just the same. But now we've talked about the past and the future, but I've got to go and look at something that's happening right now in the present.
I'm sure you do, Dr. Dick. Meanwhile, I'm going to look at the ground, of which I am very fond. John, we've been flying a long time. A lot of us getting a little tired. I assume Spire is not getting tired.
Oh, it's going along fine.
Do you know where we are?
Right now, we're about 60 miles from Los Angeles.
You've got no doubts about this.
No doubts whatsoever.
We're coming in on time, ahead, behind.
Coming in just about on time, about the way we planned it, and we're on course.
Later on, after you've had some sleep, I suppose you put all these figures together and you have a minute-by-minute story of Spire's whole performance. Is that right?
That we do. It's quite a task. Imagine we'll wait till tomorrow before we tackle that.
Don't do it tonight.
No, that we won't.
Chip, this is John. We have 15 minutes to target. Chip, 10 minutes to target. Five minutes to target. Chip, this is John. We are approaching target. Coming up on target. Over target.
Spire says we're coming into zero, we're coming into target, and Spire is absolutely right. The clouds are breaking now, and we're coming in right over part of Los Angeles. I can see the city squares and the highways and the streets very clearly through the very sparse clouds. Spire has been on the dot so far as I can tell. I cannot tell you whether it was supposed to take us right to a runway, to an airport, or to the city area generally. That's highly classified information, the precise accuracy of the instrument. All I know is that the sun is shining on Los Angeles. It's right down below us. The machine says we're here. We all know we're here.
That's it, Chip. It's your airplane.
Roger, John. Thank you. Okay to remove Spire. Take over manually.
Goodbye, John.
Hey, Rick.
Thank you. Chip, thanks so much.
Pleasure having you.
Dave.
Thank you.
And Dr. Draper. Long ways from MIT, sir.
Sure is.
Thanks so much for letting us come along.
Come along anytime. It's a lot of fun to have you.
We will. This has been an extraordinary journey, courtesy of Spire. For me and the Conquest crew, of course, this has been mostly an adventure. For Dr. Draper and his colleagues, this has been a test, and a successful test, of the theories and the engineering that made Spire possible. And maybe one could say this is one small step toward the age of space travel. Next, a report from Monsanto.
Conquest with Eric Severide was presented by Monsanto Chemical Company. This is Nelson Case speaking for Monsanto, where creative chemistry works wonders for you.